This lecture is about the kinetic model of an ideal gas. This is introducing the idea of what an ideal gas is. This is a summary of all the information we'll be going over. And this is the kinetic model of an ideal gas itself. These are all the requirements for a gas to be an ideal gas. As a reminder from a previous lecture, internal energy in particles in a material can be either kinetic energy of the particles or potential energy in the bonds between particles. Adding kinetic energy increases the temperature, and adding potential energy decreases the strength of the bonds between the particles. So both of these are examples of internal energy, energy contained within the particles of an object. If that internal energy is kinetic, it goes into increasing the temperature of the material, and if it's potential, it goes into changing the phase of the material, but doesn't change the temperature. We're now ready to talk about what an ideal gas is and what a non-ideal gas is. So this is the fundamental property of an ideal gas. All internal energy that we add to this gas becomes kinetic energy. So there's a linear relationship between internal energy added and temperature. So if we have an ideal gas, what it means for the gas to be ideal is that if we add any energy to the gas, all of that energy becomes kinetic energy in the particles. And because all of the energy becomes kinetic energy, and adding kinetic energy increases the temperature, any increase in internal energy must also increase the temperature. If you look at my animation on the left, you can see that as I add internal energy to the particles, their velocities go up, and therefore their kinetic energy goes up, and the temperature goes up. And this is just consistent no matter how much internal energy I add. There's never a point where that internal energy does not also add to the temperature. So this means there's a linear relationship between the internal energy and the temperature. If I add more to one, I add more to the other as well. If a gas meets that property, if all the energy added goes into kinetic energy of the particles, we say that that is an ideal gas. That's what we mean by an ideal gas. In comparison, in a non-ideal gas, some internal energy added becomes potential energy in the bonds between particles, so there is a nonlinear relationship between internal energy added and temperature. So if I start to add internal energy to this non-ideal gas, some of it becomes kinetic energy, but some of it may randomly go into the bonds between particles instead. And I can't predict whether the internal energy will become kinetic energy or potential energy. Watching that animation again, you can see that as I add internal energy, it's going into kinetic, but then it randomly decides to go into potential and then adds a little more into kinetic. But the relationship between the internal energy added and the kinetic energy of the gas is not linear. If I increase the internal energy, it does not necessarily increase the kinetic energy. A non-ideal gas is more difficult to predict in that way because we can't know what the energy will do when we add it to the non-ideal gas. So that's why we call it non-ideal, because in an ideal world, a gas would be very easy to predict and understand. So a non-ideal gas is more difficult to predict because we don't know what the energy will do when we add it to the gas. Just to reinforce this a little bit more, in an ideal gas, all of the energy added becomes kinetic, and in the non-ideal gas, the energy can either become kinetic energy or it can become potential energy and break down the bonds between particles. So that leads to the question, what properties must an ideal gas have so that all energy added becomes and remains kinetic energy in the particles? There's a whole list of properties, but these are the two properties that it's most important for an ideal gas to have so that all the energy added becomes kinetic energy. The first property is there can be no intermolecular forces or bonds between the particles. If there were intermolecular forces or bonds between particles, some of the energy added would go into breaking up those bonds. It would become potential energy instead of increasing the velocity of the particles, which increases the kinetic energy. So a situation where there are no bonds at all between the particles that means this could be an ideal gas. And if there are intermolecular bonds, that's bad. And that means that this is not an ideal gas. The second requirement for all the energy to become kinetic energy is that all collisions between particles and between particles and the barrier must be perfectly elastic. Because perfectly elastic collisions are the only type of collision where the total kinetic energy remains constant. If an inelastic collision occurred, some kinetic energy would be lost from the gas. So if the particles are colliding, they have to have a perfectly elastic collision. They can't stick together at all. And if the particle collides with the barrier that's holding the gas, it also can't stick to the barrier at all. It has to be perfectly elastic and bounce back in the opposite direction. If any kind of inelastic collision occurs, some kinetic energy is converted to other types of energy, and it no longer exists as kinetic in the gas, which means that the energy added wouldn't necessarily remain kinetic energy. There's a common comparison made between particles in an ideal gas and billiard balls. Particles in an ideal gas behave just like billiard balls rolling on a table. There are no forces holding them together, they just kind of roll in random directions. So because there are no forces holding them together, they meet that first requirement for an ideal gas. And all of their collisions are also perfectly elastic. They always bounce off each other and never stick together, and never stick to the edge of the table either. So if you're having trouble remembering the properties of an ideal gas, the billiard ball example might help. The particles behave just like they were a ton of billiard balls bouncing off each other. So again, the reason why we call this the kinetic model of an ideal gas is that it's saying that the fundamental reason we call gas ideal is because of something related to kinetic energy. All the energy going into it has to be kinetic energy. There are implications of these assumptions, and you're expected to memorize these properties of an ideal gas for this course and for the IB test. I won't read these all out, but these are the properties of an ideal gas that you're expected to memorize for this class. All gases in the real world are non-ideal. There's no such thing as a real, true ideal gas, which means the particles in them have some intermolecular forces, and some of the collisions of the particles are not perfectly elastic. Gases behave more like ideal gases when the particles have a lot of kinetic energy compared to potential energy, because most of the energy going in becomes kinetic rather than potential. This occurs at lower pressures, lower densities, and higher temperatures of the gas. The more a gas behaves like an ideal gas, the more easy it is to predict its behavior mathematically. So the more that a gas has these properties, the better that is for us as scientists, because we want the gas to be more predictable and understandable. So if the gas has more kinetic and less potential energy, it behaves more like an ideal gas. And if it has less pressure, more temperature, and less density, it also behaves like an ideal gas. This is because higher temperatures mean more kinetic energy, and lower pressure and density means the particles are interacting with each other less and thus not applying as many intermolecular forces. This is another common test question where you are expected to know the situations where a gas behaves as an ideal gas. So again, that's when the particles have more kinetic energy, less potential energy, less pressure, more temperature, and less density. Those are the conditions for a gas to behave more like an ideal gas, which is easier to understand and predict. So that's everything that you need to know about the kinetic model of an ideal gas. This is a summary of everything that I talked about. And again, this is a list of the properties of an ideal gas as implied by the kinetic model that you're expected to memorize and understand for the rest of the course.